All right, let's dive in. Today we're tackling calculus. Using Calculus Made Easy as our guide.
Okay.
You sent in some excerpts from the book, and I'm guessing you're either just wanting to brush up on the basics or maybe even get ready for a calculus class.
Right.
Don't worry, we're here to make even the trickiest concepts, make them click.
Yeah, that's right. Calculus Made Easy. It's really famous for its approachable style.
Yeah.
It's been helping people understand calculus for like over a century.
Over a century, that's incredible.
Mm-hmm.
So, okay, let's just start with the big question. What is calculus, really? I mean, it's got this kind of reputation for being super complex.
Yeah, it's funny. Calculus does often get overcomplicated.
Right.
But at its heart, it's really just, it's the math of change.
Okay.
I mean, you think about how a roller coaster speeds up,
Yeah.
as it goes downhill, or how a plant grows taller over time.
Uh-huh.
Calculus gives us the tools to analyze those changes precisely.
So it's not just about describing change, but it's about, measuring it, predicting it.
Exactly. And it does this through two main branches: differential and integral calculus.
Okay.
Differential calculus kind of zooms in on instantaneous rates of change.
Okay.
So imagine freezing a roller coaster mid-descent.
Right in the middle of that drop.
Yeah. Differential calculus helps us figure out its exact speed at that very moment.
Oh, okay. I think I'm starting to see the picture now.
Yeah.
What about integral calculus? What's its specialty?
Integral calculus is all about adding up tiny pieces to find the whole.
Okay.
So think about the distance the roller coaster travels along its entire track.
Mm-hmm.
Integral calculus allows us to calculate that total distance by summing up all the tiny bits of distance it covers moment by moment.
So differential calculus is kind of like taking a snapshot.
Yes.
And then integral calculus is like adding up all the frames of a movie.
That's a great analogy.
Oh, good. I'm glad I got one right.
Now, one of the things that makes Calculus Made Easy so unique is how it explains these concepts without relying heavily on this complex idea of limits, which could be a major stumbling block for beginners.
Yeah, limits always trip me up in school. I get the general idea,
Right.
but the formal definition always made my head spin.
Yeah.
So how does this book manage to sidestep that?
Well, the author, Sylvanus Thompson, he uses a system of approximation that makes the core ideas of calculus much clearer.
Okay.
He breaks down complex processes into smaller, easier to grasp steps.
Right.
It's he's giving you this behind-the-scenes look at how calculus works without, overwhelming you with too much technical jargon.
That sounds much more welcoming.
Right.
Yeah, definitely. Speaking of making things easier, you mentioned Zeno's paradox a little earlier.
Yeah.
It's that mind-bending thought experiment about a runner who never seems to reach the finish line because they're always having the distance, right? What does that have to do with calculus?
Zeno's paradox. It's a clever way to illustrate the concept of a limit, even though the book doesn't explicitly focus on them.
Okay.
So imagine our runner on a 100-meter track.
Okay.
First, they run 50 meters, then 25 meters, then 12.5 meters, and so on.
Uh-huh.
Zeno argued that, they would never actually reach the finish line because they'd always have half the remaining distance to cover.
Yeah, I remember wrestling with that paradox in philosophy class. It just feels like the runner should reach the finish line eventually.
Yeah.
But the logic of having the distance, it seems inescapable.
That's the beauty of it. Zeno's thought experiment, it highlights how our intuition about continuous motion, it clashes with the idea of infinite steps. Okay. What calculus does is it provides the mathematical tools to bridge that gap.
Okay.
It allows us to analyze change not as a series of discrete jumps, but as a smooth, continuous flow.
So even though the runner keeps taking smaller and smaller steps, calculus helps us see that those steps blend together into a continuous path that does indeed reach the finish line.
Precisely. And this ties into how calculus handles real-world phenomena that don't happen in neat, discrete steps.
Okay.
Think about a plant growing.
Uh-uh.
It doesn't suddenly sprout an inch taller every hour.
Right.
Its growth is, a continuous unfolding process.
Right.
Calculus helps us to understand and model that kind of change.
That makes a lot of sense. Now, the excerpts you sent in also mention a bit of a debate going on in the math world about which theorem to teach first.
Oh, yeah.
The mean value theorem or the increasing function theorem.
Ah, yes. That's a fascinating discussion. It reflects how math education is always evolving.
Mm-hmm.
The increasing function theorem, or IFT, was a great example of how calculus connects to real-world scenarios.
Okay.
Think about designing a roller coaster.
Okay.
You want to make sure the climb up the hill is continuous, meaning the roller coaster never unexpectedly goes backward before the big drop,
Right.
The IFT provides a mathematical guarantee of that continuous upward motion.
So it's like a safety check for roller coaster designers.
Right.
Making sure the thrills happen in the right order. That's interesting how even the way we teach calculus is subject to change and debate. And I guess that's how any field stays dynamic and relevant, right?
Absolutely. And speaking of staying relevant, you also sent in a snippet about Duke University students who seem to prefer good old-fashioned pencil and paper over computer-based calculus.
Yeah, I was surprised to read that.
Yeah.
You would think with all the technology we have today that, computers would make learning calculus a breeze. What's your take on that?
Well, I think it's an important reminder that technology, while powerful, shouldn't replace deep conceptual understanding.
Right.
Computers are great for crunching numbers and creating visualizations.
Sure.
But they can't replace the aha moments that come from grappling with ideas and making connections on your own.
Yeah.
It's like, learning to play the piano. A synthesizer with auto accompaniment might be fun, but it won't teach you the fundamentals of music theory or how to truly master the instrument.
I like that analogy.
Yeah.
It's about building that solid foundation of understanding and not just relying on shortcuts.
Exactly. And with that foundation in place, technology can become a valuable tool for exploring calculus further and applying it to real-world problems.
Right.
But without that core understanding, it's easy to get lost in the sea of equations and symbols.
Okay, I'm convinced. So, we've got a sense now of what calculus is all about, but let's break down some of the key concepts. I think a good place to start is with derivatives, which seem to be at the heart of differential calculus. What exactly are they, and how do they work?
Derivatives. They sound kind of intimidating, right? But think of it this way. They're just a way to measure how fast something is changing at a specific moment. Like, picture our roller coaster again. As it plunges downhill, its speed is constantly changing. The derivative tells us exactly how fast that speed is increasing at any given point.
So it's not just about the speed itself, but like how quickly the speed is changing. That's a subtle but important distinction.
Precisely. And what's fascinating is that a derivative itself is also a function.
Okay.
It's a function that describes the rate of change of the original function.
Okay, so
It's like a layer deeper, giving us more nuanced understanding of how things are behaving.
Gotcha. Okay, so we've got change and rates of change. And Thompson's book also talks about constants and variables. Can you remind me how those fit into the picture?
Yeah, of course, constants are the fixed values in a situation. Like the length of the roller coaster track or the gravitational constant variables are the things that change. Like the roller coaster's position on the track as it moves or the speed it picks up as it descends.
I remember struggling with that distinction in school. I used to mix them up all the time. It wasn't until I started thinking about constants, like my own height, unfortunately a constant I can't change, that it finally clicked.
That's a great way to think about it. And calculus is all about understanding how those variables change in relation to each other. And to express those relationships, we use the powerful concept of a function.
All right, let's talk functions. Break it down for me. What are they all about?
Think of a function as a relationship where one thing depends on another.
Okay.
For example, the height of a sunflower depends on how long it's been growing.
Okay.
The longer it grows, the taller it gets.
Yeah.
That relationship is a function.
So it's like a cause and effect relationship almost, like the amount of sunshine a sunflower gets affects how tall it grows.
You got it. And in that example, the height of the sunflower would be the dependent variable because it depends on the amount of sunshine it receives, which is the independent variable. The amount of sunshine changes on its own, and the sunflower's height responds accordingly.
This is making a lot more sense now. I can see how functions are everywhere, even in nature. Like the temperature of a cup of coffee depends on how long it's been cooling.
Exactly.
Yeah.
And, to make these functions easier to visualize and analyze, we often plot them on something called the Cartesian plane.
Ah, the Cartesian plane. That's that grid with the X and Y axes, right. I remember seeing it in math class, but never fully understanding what it was for.
It's basically a visual tool that allows us to represent functions as graphs.
Okay.
So instead of just having an equation, we get a picture of how the function behaves.
Okay.
Imagine plotting the height of our sunflower over time.
Oh, okay.
We could mark the days on the x-axis and the height on the axis, and each point on the graph would represent the sunflower's height on a particular day.
Oh, I see. So we'd get like a curve showing how the sunflower grows taller each day.
Exactly. And, this ties back to what we were talking about with derivatives. Remember how the derivative of a function tells us about its rate of change? Well, on the Cartesian plane, the derivative is represented by the slope of the function's graph.
Wait, hold on. I'm trying to picture this in my head, like how a runner's changing speed would look on a graph. Would their derivative be all over the place as they speed up and slow down?
That's a great question. Imagine plotting the runner's position on the axis and time on the x-axis.
Yeah.
If they're speeding up, the graph of their position will curve upward more and more sharply, representing a steeper and steeper slope. As they slow down, the curve flattens out, representing a shallower slope.
So the steeper the curve, the faster the rate of change, and therefore the larger the derivative.
You nailed it. And to really see how the derivative works at a specific point, we use the concept of a tangent line.
Tangent line. Now that rings a bell, but I need a refresher. What are those again?
Imagine a tightrope walker on a curved wire. Their balancing pole as it touches the wire is like a tangent line to a curve. It touches the curve at one point and gives you a sense of the curve's steepness at that exact spot. The angle of the pole represents the slope of the tangent line, and that slope tells us how steep the curve is at that specific point.
That's a great visual. So the tangent line basically captures a snapshot of the function's behavior at a single point.
Precisely. And the slope of that tangent line is exactly what the derivative of the function represents at that point.
So we can use tangent lines and their slopes to visualize how the derivative of a function is changing from point to point. I'm starting to see how all these pieces fit together.
And this idea of slopes and derivatives is essential for finding what we call the maxima and minima of a function.
Maxima and minima, are those like the peaks and valleys of a curve?
You got it. Think about the highest point on a roller coaster track, or the lowest point of a valley. At those points, the curve momentarily flattens out, meaning the slope of the tangent line, and therefore the derivative is zero.
So by finding where the derivative is zero, we can pinpoint those peaks and valleys. That's amazing. I can see how that would be useful for all sorts of things, like optimizing the design of a roller coaster for maximum thrills.
Exactly. And this leads us to the other side of calculus, integral calculus, which, as we discussed, is all about adding up tiny pieces to find the whole.
Okay, I'm ready to dive into the world of integrals. But before we do, can you remind me how integration relates to differentiation? I know you mentioned it earlier, but I need a quick recap.
Of course. You can think of integration as essentially hitting the undo button on differentiation. Remember how we took the derivative of a function to find its rate of change? Well, integration allows us to work backward from that rate of change to figure out what the original function was, or at least a family of functions that could have that derivative.
So integration's like working backward through a math problem to find the original equation. That sounds handy, but I bet it's not always that straightforward.
You're right, it can get quite tricky. But one of the most powerful applications of integration is finding the area under a curve.
Finding the area under a curve. That sounds a bit abstract. How does that connect to the real world?
You'd be surprised how often this seemingly abstract concept pops up in real-world applications. For example, imagine you're a physicist studying the motion of an object. The area under the curve of its velocity time graph actually represents a total distance the object has traveled. Or imagine you're an engineer designing a dam. The area under the curve of the water pressure against the dam wall can be used to calculate the total force the dam needs to withstand.
Wow. I never thought about how much math goes into something as simple as an object moving or water pushing against a dam. It seems like calculus is lurking everywhere, even in places you wouldn't expect.
It truly is. And just like with differentiation, there are various techniques for integration depending on the complexity of the function you're dealing with. We won't get into the specifics here, but just know that integration can get quite intricate and fascinating.
Okay, my brain might need a break after all that. But before we wrap up our calculus adventure, I'm curious about something I read in Thompson's book. He talks about dodges, pitfalls, and triumphs in calculus. Can you tell me more about that?
Calculus is a powerful tool, but like any powerful tool, it can be misused or lead to unexpected results if you're not careful. Thompson uses the term dodges to describe clever techniques for avoiding common mathematical traps.
So it's like knowing the tricks of the trade to prevent mathematical mishaps.
Exactly. And as for pitfalls, well, sometimes applying calculus rules blindly can lead to nonsensical results. That's why it's so important to have a deep understanding of the concepts, not just the formulas.
So it's not just about crunching numbers, but knowing when and how to apply the right tools for the job. What about the triumphs? What are some of the most rewarding aspects of working with calculus?
The triumphs are the incredible insights and solutions that calculus has provided to problems that would be impossible to solve otherwise. Thompson has a beautiful way of describing it. He compares a solution to a calculus problem to a butterfly emerging from a caterpillar, highlighting the unexpected beauty and elegance of the results.
That's a fantastic analogy. It sounds like working with calculus can be a truly rewarding experience filled with moments of both challenge and discovery. Wow, I feel like we've only just, scratched the surface here.
Yeah.
But this deep dive has already given me a whole new appreciation for what calculus can do. It's amazing how something that seems so intimidating can actually be so elegant and, dare I say, fun.
I'm glad to hear that. And, Thompson's approach in Calculus Made Easy really does a brilliant job of demystifying these concepts. He shows that calculus isn't some esoteric branch of mathematics reserved for just a select few.
Right.
It's a powerful tool for understanding the world around us, accessible to anyone willing to put in the effort.
It's like he's giving you the keys to a whole new way of seeing things. We've talked about roller coasters and sunflowers and even pushing boxes across the floor. It seems like calculus is everywhere once you know how to look for it.
That's the beauty of it. Calculus gives you a lens to see the patterns and relationships that govern everything from the motion of planets to the growth of populations.
Yeah.
From the spread of diseases to the flow of traffic.
It's mind-boggling to think about all the ways that calculus is being used to solve real-world problems right now as we speak.
Absolutely. And even if you're not planning to become a mathematician or a scientist, having even a basic understanding of calculus can enrich your understanding of the world.
Mm-hmm.
It can help you appreciate the elegance and precision of nature's designs and the ingenuity of human innovations.
So for our listener who has been on this calculus journey with us, absorbing all these new ideas and making connections, what's the one key takeaway you'd like them to remember?
Calculus is often seen as this gatekeeper to higher math and science, but as we've seen today, its fundamental concepts are surprisingly accessible. And more importantly, it's not just about abstract equations and formulas. It's a way of thinking, a way of analyzing change, and understanding the dynamics of our world.
That's a perfect note to end on. Thanks for joining us on this deep dive into Calculus Made Easy.
My pleasure.
And to our listener, we hope this has sparked a newfound curiosity and maybe even a sense of excitement about the possibilities of calculus. Keep exploring, keep learning, and who knows, maybe you'll be the one making the next groundbreaking discovery with the help of calculus. Until next time, keep those brains buzzing.